You know how to categorize a new object. So convexity helps you in offloading memory. So that's a principle of cognitive economy. So that's the first answer to why convexity. The second answer is that it makes learning much more efficient. And this is the problem I started from. How can we explain how we learn words very quickly? So assume again that we have a two-dimensional space. Now I haven't drawn the borders. And this is a learning story. Let me give you a simple story. You're a father, you bring your 2 or 3-year-old daughter to the city pond. And in the city pond, you see a lot of birds. There are some birds that are geese. There are some birds that are swans. There are some birds that are ducks. So you point to your little daughter, say that this bird, this is the properties of the bird in the bird space, whatever bird space is like. And you say that this is a duck, and that's a swan, and that's a goose, and this is a goose, and that's a swan. That's what I said. And you see a number of examples like that. And this little girl sees the empirical examples. You get these instances. And the ducks are kind of similar. They're located in this region of property space. The geese are a bit also similar, and the swans are here. Well, maybe they're even more similar. Anyway, you get a few examples of each word, and you get the locations in property space of this. On the basis of that, the girl can form an average, and the crosses are, I take a very simplistic story here, the mean of the positions in the space. And given these means, you can take the means as a prototype. And then that mean will generate a Voronoi tessellation. And if the girl sees a new object, you know what it's more similar to. It's more similar to a duck than a swan. So you know that this should be called a duck. So the point here is, once you have the space, you basically only need one example to form some kind of prototype. If the only example you've seen of a duck is this particular duck, then that will be your concept of a duck. And then you can use that to generalize.
Can I just ask a clarifying question?
Yeah.
The mean is a number. Mean means a number, right?
Yeah.
Is it, in this case, is it the number of shared features?
No, this is a number, the mean of positions. So you have positions in the space. This is positions. And I'm assuming a metrical space again, to simplify things. So it's the mean of the positions in this space.
The ducks, maybe I'm not getting it. But your girl sees the ducks.
Yeah.
What does the mean in terms of...
it has a mean average shape, it has an average color, it has an average... So it's a lot of features that determines the... But I haven't given you bird space, and that's a complicated story. But this is the general principle of learning from a few examples here. You observe the properties as a location in space. And then if you have different location in the space, you can calculate the mean of the location. So now we continue the story, and suddenly there is a new object. There is a new bird and it's a mandarin duck. It's a bit odd as a duck. It doesn't really look like it. It's a bit strange. But the father insists that this is called a duck, even if it's these hatch lines are the old categorization. So the girl now gets a new example. It's a bit odd. The mean changes. The mean moves. And that means you have a new categorization. So the point of this story is to say that the categorization is not fixed. How you categorize things is dependent on your experience. So you learn more about concepts by seeing more exemplars. And of course, if you have a rich experience, seeing a new exemplar will not move your concept very much. But if you only have seen 1 or 2 examples, you may change your borders between the concepts quite radically. So when I say that you only need one example to learn a concept, that means once you have an example, you assume that that's a prototypical one. And then from there, you go on using the word as you have done before. Go ahead.
When I see a penguin, I would not say it's a bird.
No.
You're taking some extra effort to remember, okay, it's not really, or whatever, it's a bird.
Yeah. No, a penguin is perceptually not very much like other birds. And then you have to go to other features, like it's laying eggs and it has body parts like wings and so on, even if the wings don't look like wings. I mean, you have to go to biological categories. And this is how you learn later that the penguin is a bird, because it has the right biological properties rather than the right perceptual properties.
This looks like I immediately recognize the penguin as a bird, right? Like this looks like there's no real distinction between recognizing like the typical bird as a bird compared to the penguin. So like what I meant is that I don't really go by features. I don't really go by lays eggs or something. I just think, oh yeah, I have this theory that it's probably a bird because someone told me about it. So that's a different process instead.
It's a different process, because when you start talking about the biological features of a bird, you're leaving the perceptual. I mean, in my story, I was focusing on the perceptual features of birds. But we know that there are other domains. I'll get back to that point in a little while. Yeah.
So you said, since it is all about the sum of examples I've seen, or exemplars I've seen, when I've seen a lot of exemplars and then seeing one new doesn't change as much. But I would say that if you see one that's very odd and very out of the group, it actually does change a lot.
Yeah, it does. And I can give you examples of that. I mean, people thought that all swans were white. And then suddenly you went to Australia and you found black swans. That was a big change in the concept of a swan. But there were other characteristics that decided that people still continue to call this bird a swan. Maybe mainly on the...
I would say it's not only the sheer number of exemplars I've seen, but also over time, it's different from the prototype also.
Yeah. But it's also dependent on what features, what properties, what domains are you consider to be essential, the more important for a concept. So I'll get back to that point in a while. This model also explains why children overgeneralize concepts, overgeneralize their use of concepts. Because if the only animals a child has learned is a cat and a dog, it's a city child, and it only sees cats and dogs. And then you go out in the countryside and you suddenly see a cow. What will this child say? Call the cow a dog. Yeah, it will call it a dog because it's overgeneralized. It only knows the words cat and dog. It knows it's an animal, so it will overgeneralize dog and apply it to cow. And of course, what happens then when you make finer discriminations, you partition the space more, you end up with more prototypes, and then you get the finer partition and so on. But I mean, this is a very simplistic model. I mean, I'm not saying that all spaces are metrical, that we do it by this simple mean calculation. But I mean, this simple model shows that given a spatial structure, you can explain how you can start using concepts only after one or couple of examples. And then use it in, sometimes successful, sometimes not so successful way. Okay, that's a quick learning. Now, later I will talk about the empirical support for this from linguistics. But let me skip that, save that for a little bit until I get into the word classes, where we'll see a little bit of support for convexity in concepts. I want to make, I mean, I was complaining when I talked about the symbolic approach, that everything has to be formulated as a predicate. Now I wanted to introduce a distinction. This is my distinction between properties and concepts. So this is a way of dividing predicates into two groups. So I use the notion of a property for something that is in one single domain. So red is a property because it relates to the color domain. And big is a property because it relates to the size domain and so on. Then concepts for me are something that is more complicated, may have more regions. Like when I talk about animals or fruits or, ordinary objects, they have an animal has a size and a shape and a sound and a smell and a weight and a temperature. I mean, it has properties in lots of domains. So I want to define I should say object concept basically as a set of convex regions in a number of domains, and then some information about which domains are the more central ones. I mean, some of them are not so important for the identifying the concept. Some are more important. I'm not really an essentialist, but it's something like an essence idea of a concept. And then also we have information about how the domains, regions in different domains are correlated. So let me give you an example here. Let's take the concept of an apple. So when you're a kid, you learn about the color of apples. They are red, green, and yellow. You never see blue or black apples. And you have taste spaces, 4-dimensional. You have sweetness, sourness, bitterness, and saltiness. Maybe an umami taste as well, if you like. But basically, apples go by or have values for sweetness and sourness. That's where you find them. You can have more or less sweet apples and so on. Shape space is a bit complicated, but sorry, that's the shape space. Let's go back. So it's in the round radius shape space. The major distinction between apples and pears is the shape, I mean the color and other things. And then when you learn more about apples, you learn, I mean, as an adult, you learn about the nutrition of it. If you become an expert, if you become a pomologist, as they are called, you learn about skin type and seed type and, I don't know, flesh type of apples. A lot of finer domains that you add to a notion of apple. The point here is that a concept is an open thing. You can add more domains, more knowledge about the concept. But once you encounter an apple, you have the perceptual properties of the color and maybe the taste and the shape of the apple. That's the first domains you pick up as a child when you learn about them. But concepts are open-ended. I'm not talking about necessary and sufficient conditions here. So shape space is very interesting because we can very easily identify shapes, but we don't know how we do it in our brains. And there are a number of shape theories. This was the first one that was presented by David Moore in the early 1980s, where he'd used cylinders as a kind of building blocks for shapes. Actually, he used generalized cylinders. And the point here is that a cylinder you can describe with two coordinates, its length and its thickness. And then you can talk a little bit about how these pieces are put together. I mean, you can define this as a kind of multidimensional vector, each of these things. So that Mars representation clearly defines a shape space, I mean, in terms of the thickness and the length and the angles and connection points and so on. But then this is maybe not the best representation of how we perceive shapes. There are other theories. I don't want to get into that. But we are using shape information, in particular as children. I mean, Linda Smith has shown that there is this very strong shape bias in how children learn object concepts. So shape is very important for early concept learning. Then we give up the shape importance later. So let me go back to my... I should go back to this idea. So this is what I mean by the prominence values. They change over time as you learn more about the concept. I didn't say anything about information about how the regions... Of course, there is a correlation between the color of an apple and the sweetness of an apple. Red apples tend to be sweeter than green apples. We all know this. We expect the red apples to be sweeter than the green ones. So we know something about that. I've forgotten who... I have an example, but I've forgotten where it comes from. But the example is the following. You somehow end up in an island, in an unknown place. And on this island you meet one person. The person is a man, the person has a brown skin, and the person is very fat, is obese. That's the only person information you have. You have one example. Now, I ask you to estimate the probability that the next person you meet on the island is a man. What is the probability the next person on the island you meet is a man? Come on. Give me a number. 50%, yes. Correct answer. Almost, around 50%. Very narrowly you would get that kind of estimate. Okay, what is the probability that the next person you meet on the island has a brown skin? Come on.
51. How many skins are there?
Yeah.
How many skins
1, okay. Now, if you do this experiment, you normally get an answer like 0.8, 0.9, I mean, higher up. What is the probability that the next person you meet on the island is obese, very fat? No. It's, you only have one observation. You have to guess about the next person. What is the probability? And if you do this experimentally, you get a very wide distribution, anything from 0.1 to 0.99. I mean, it's very unknown. The point of this example is that we know that biologically there are good reasons for why the population on an island should be distributed almost 50-50 in terms of sexes. May not be so, but we still guess it. Skin color of a person is probably fairly constant, but there might be exceptions. But I mean, the point of this example is that you have one individual, and that's enough to give you a fair amount of estimates of what is the probability of that feature of other individuals. But the probability depends on the feature, of course. Okay, that's what I wanted to say about the correlation about the regions here. Okay, now that's the end of my introduction to conceptual spaces and semantic domains. Now I want to get into semantics as a meeting of minds. And now we get entertainment or something at the same time. I would like to say that there are two kinds of, when we communicate, there are two processes. One is slow. One is fast and the other is slow. The fast one is when we draw attention to the same thing, when we have joint attention, or when we build up, in the dialogue, we build up a common ground. I mean, I'll tell you what common ground is very soon. And the slow process is when we talk about how we correlate the meaning of words. In linguistics, this is sometimes called the distinction between the pragmatics of communication, and this is the semantics of communication. But I don't think there is a very sharp border between semantics and pragmatics. The idea of common ground I take from Herbert Clark. And when you start talking, having a discussion with a friend, you're telling a story, giving some gossip, giving advice or whatever, in the dialogue, you introduce a number of references. You start talking about the person, you start talking about an event. And as the dialogue proceeds, you build up a common ground of reference, of actions, of events and properties that you have mentioned. And you can build on that. And in particular in the use of pronouns, you build on that. I mean, I talk about the man I met on the street with his strange hat. And then I say he was very old, and so on. And this meaning of he refers back to a reference. So pronouns builds on this kind of common ground. And we have all kinds of demonstratives and other words that really builds on this kind of fast process of building up shared information. This is exactly what I just said, that you accumulate during a dialogue. And it's also been shown that you design your utterances. I mean, I wouldn't use the word the man unless I've already introduced him. Otherwise, I would say a man. I met a man on the street, and so on. Using the indefinite marks that this is unknown to you, and the definite marks that I've mentioned this before. You should know who I'm referring to. So we have determiners as part of this. I don't want to get into the details here because it's not really semantics. But now I want to talk more about how we can make minds meet. And actually convexity plays a role here. And I'm getting back to this problem here. How can we share mental representations? And the famous case is Humpty Dumpty, who says that whenever I use a word, it means just what I choose it to mean, nothing more, nothing less. And then Alice protests and says that the question is whether you can make words mean that things. And normally we don't go around as Humpty Dumptys. I mean, we don't assume that when I use a word, you know what it means. I'm playing on some kind of common usage of words here. So the question is, why are we not all Humpty Dumptys? That's what I want to answer. And I've developed a model together with my colleague in Venice, Massimo Vaglian, that we call a model of fixed point semantics. And I mean, sharing meanings is a little bit like reaching agreement on a contract. We negotiate meanings rather than, well, sometimes I decide what the word means and you don't have anything to say. But typically, if we don't understand it, we negotiate meanings. And here is a very abstract definition of a semantics. And a semantics is a function that maps a word or a communicative expression on some kind of mental state. I say something, you form a mental state. And then we have the converse thing. I have a mental state and I turn it into an expression, a word. So the semantics is this two-way mapping between semantics and mental expressions. But in terms of a dialogue, it works like this, that I have a mental representation of a color green. And then I say the word green, and you listen, and you form a mental representation of what I'm saying, and then you say, okay, green. And then I understand that this gets back and forms a mental representation in my mind. And if this ends up at the same place as my original statement, then it is a fixed point. I mean, the communication should be what is called a communicative mapping here. So that's the idea of sharing meanings. But the problem is a little bit, little bit more complicated. So minds meet when this function maps states of mind on states of mind, when there is a fixed point. This is what I tried to illustrate with the previous picture. Come on. And the way we model is as equilibria in communication games. Now, lots of people have talked about language games. It started with David Lewis and so on. But what we do is to add some kind of topology and geometry to these mental states. I mean, this is the conceptual spaces. And we show that addition will help in generating fixed points. Before I get to the general argument, I will illustrate this with an example that is taken from a work by a communication game studied by Gerhard Jäger and Robert van Rooij some years ago. And their game is, you have a space. They call it the color space, but it has nothing to do with colors, really. They have a space of colors. In mathematical terms, it's compact and convex, doesn't matter. And the signaler has a finite number of messages. These messages are originally just tokens. You can choose between A and B, or between A and B and C, or between A, B, and C and D. You have a small number of messages. And at the beginning, the receiver knows nothing about what is the meaning of A or B or C. So it's totally unknown what the messages are. And then the game proceeds as follows, that nature, that is a computer, selects a point in the space. The sender selects one of the messages, and the receiver listens to the message, and then the receiver points to a point in the space. And the game is such that the closer the receiver points to the original point, the more the sender and the receiver are rewarded. So it's a cooperative game. The sender is saying A, B, or C, or D, and the receiver has to guess what is the original point in the color space. Of course, at the beginning, everything is random, but soon, or not soon, but after a number of iterations, they will converge on this is what I just said. So this is the results of the simulations. At the beginning, everything is random. If the sender has two messages, they are either A or B, then you end up with a solution like this. I mean, a stable state, an equilibrium in game theoretical terms. And whenever the signaler says A, the receiver will point to this point. Whenever the sender says B, then the receiver will point to this point. And these points have the property that they minimize the average distance within the regions. So that's a mathematical property. They minimize the average because they're rewarded for being as close as possible. So if you point to the middle point here that minimizes the average distances, you get the maximal reward. That's the reason. So they've done computer simulations showing that this is what you end up with. And this is actually, they can show, yeah, I'm getting back to this now. They're rewarded for this similarity. And they show that there is a Nash equilibrium, this is a game theoretical term, that is a Voronoi tessellation. You end up with a Voronoi tessellation of the color space in this communication, if you have a finite number of signals. Now, this is dependent on the notion of similarity. You're rewarded for how close you come to the points. So that's the way in which the geometry comes into the thing here. And the fixed points then, I mean, these points can be seen as the prototypes, the points that are the central points here. Because if nature selects this point, then the sender will say A, I mean, corresponding to the red region here, and then the pointer will point back to that fixed point. So the prototypes turn out to be fixed point in this communication here. So that's their model. Now, there are a couple of assumptions here. First of all, that they all have the same space. And that's not always the case. I mean, I may have one space, you may have another one. How can we make sure that we can find a shared meaning here? So I say this is somehow coordinating the meaning of words. That's one thing to notice is that there is no unique solution here. Any rotation of a solution will also be a solution. So there is no unique outcome of it. You can rotate the prototypes. But if you interact, if you communicate a large number of times, you will agree on where are the fixed points, where are the prototypes. And that becomes then the meaning of the messages A, B, and C in this artificial example here. What Massimo and I did was to generalize this example. So I don't want to spend time on this because it's a bit of mathematics. But now we don't assume that we have the same space. They can have different spaces. It doesn't have to be the same. And we only assume that these spaces are convex and compact. Don't bother. If you know the math, it's okay. If you don't, it doesn't matter very much. The product space will also be compact and convex. You have this representation interpretation function. That means going from one expression to the minds of the other and then going back again. So it's officially mapping from C to C, I mean the product space. We assume that the mapping, this kind of mapping, is continuous. And this assumption of continuity means that if two positions in the space are close enough, that means, well, they are similar enough. But then they should also be called by the same name. So this is a very strong and natural assumption of words. Things that are similar in some kind of space are called by the same word, fall under the same concept. That's an assumption that we formulate as continuity. I mean, that's what it boils down to in mathematical terms. So this is a way of saying that language preserves these similarity relations by sorting. I mean, a word brings similar things together. That's the meaning of continuity here. And then we use this fixed point is the definition. Then we use a famous theorem by Brouwer saying that every continuous map has at least one fixed point. This means that if we have satisfy these conditions that I just gave you, then there will exist a meeting of minds. Now the interpretation of this is that if individual meanings are well shaped, that means convex and compact, then, and if language is plastic enough to preserve the spatial structure of concepts, that means similar things are fall under the same concept, there will exist a meeting of mind. I mean, this is what Brouwer's fixed-point theorem says. We can solve this problem of coordinating our minds. This result doesn't say anything about how we do it. It just shows that if we have these kind of structures, convex and compact and so on, then there exists a solution. We can find it. We can agree on a solution. Then, of course, there is a long history on how we find a fixed point, and we come into a language, we were born into a society where already language exists. But language is flexible, meanings change slowly over time, and so on. What language is doing is preserving neighborhoods. I mean, I have my interpretation, I can choose between a finite number of words, and we have to map it onto your space. But it will preserve neighborhoods. So if points are similar here, they will be mapped to similar points over here. That's what meant by continuity. So a continuous function mapping a meaning space is compatible with that we only have a finite number, a discrete number of signals. And that's how language works. We don't have a continuous set of expressions. We have finite number of words, even if there are quite many. Of course, this process is not perfect. I mean, here's the story of the tourist coming and asking the police for the way to the museum, and the police starts saying that walk to the next red light and then to the traffic circle, turn right, turn left at the next traffic light, blah, blah, cross the railway. You get this, and then you have to translate it back into a spatial representation, and this doesn't work. I mean, this mapping is not perfect, but we still can work by it. We can make approximations of it. So, to sum up, this, I've given you let me do it. So I've given you a model of how we can share meanings based on this kind of communication, where we are rewarded for solving, so to speak, having the same meaning of a word, a concept. So the meanings emerge through the interaction between the members of a linguistic community. Meanings of language is not given by God or by anybody else. I mean, it's a kind of emergent phenomenon that results from a lot of communication between people. And language is a game where we can fail or succeed and so on. Of course, we can lie as well, which is another part of game theory that I don't want to get into. Semantics is a fixed point for the game. That's what I talked about. Now, we had a question earlier whether this semantics is independent of reality. The concepts are mental constructs. They are generated by communication. But reality comes in by to tell whether you succeed in your coordination or whether you fail. So, to give you a simplistic example, assume that we are on a bad telephone line. We agree. We need to agree. A very important meeting. So we agree that we meet in the student union in Cambridge next Tuesday, and then the telephone line breaks down. Now, if you go to Cambridge, England, and I go to Cambridge, Massachusetts, and you go there Tuesday, 5 days from now, and you go there Tuesday the following week. I mean, there is next week maybe we totally fail in coordinating our actions. I mean, we use the word Cambridge and next week in two different ways. So then we have to adjust. We have to negotiate. By Cambridge, we mean Cambridge, England, and nothing else, and so on. So this is where reality hits back. When communication fails, we have to renegotiate and readjust our concept. We have to find a fixed point that we agree on. And then that we agree is shown by that we succeed in coordination. I hope that you hear that I'm not using the word truth anywhere here. I mean, you can't hear that I'm not using it. But anyway, I want to emphasize, this is a pragmatic theory. I get the meaning via the successes and failures in interactions. And the successes and failures is where the world gets into the determination of the meanings. So this is a good place for me to stop for questions. Yeah, go ahead. Yeah. So,
does this theory have to say anything about it?
Not very much. I mean, the colorblind example is exactly Putnam's example of beech and elm, because Putnam is not colorblind, but he's tree blind, so he can't distinguish between beeches and elms. But he knows that there are these words, and colorblind people knows that there are words like green and red and so on. They can learn by using these correlations between domains to use color words fairly accurately. I mean, they can distinguish between. I mean, they can't distinguish between a green and a red apple, but there might be other aspects of the apple that correlates with these color words. So, colorblind people can actually learn to use color words by exploiting the correlations with other domains. That would be my answer to your question. Yeah.
I have a question about how, let me pick the right word, concepts or spaces are relating to each other. So, I mean, I know you just use it as an example, but let's, so you said whatever bird space looks like.
Yeah.
So here's a question: does bird space contain penguin space? Or is bird space contained in blue space? So did you see the question?
Yeah. Sure. Yeah. No, penguin space is the same as bird space. That there is a number of features that all the bird space. Thing space has many other domains that bird space don't have. I mean, so it's a question of what domains you include in the space you're talking about. That would be so. Penguin is a sub-region of bird space. It's out in the corner somewhere because in the prototype they fly and they sing and they build nests, but penguins don't do that.
So it seems like for the conceptual spaces, the examples that we look at so far are very focused on where the dimensions would be very linked to perception.
Yeah.
Is that so? But then, so for the example you gave, the symbolic approach is represent something like grounding. Do you envisage representing these kind of concepts?
Yeah, I'll give you this example in a little while. I mean, you're perfectly right. I focus on perceptual domains because we know something about the structure of color space. We know how size, space, and temperature. I mean, we know these perceptual properties. When it comes to more abstract things, we don't know very much. But you mentioned kinship, didn't you? Yeah, and kinship is a good example. I'll actually give you kinship space in sometime when I don't know when, but it will come.
I kind of had a follow-up because I just don't see how you have this. You pointed out this problem with the symbolic approach that you have to know what the primitive is. But we not run into the same problem trying to pick dimensions.
Partially, but again, I think I will answer your question as I go on. Yeah.
Could you please explain to me the difference between the coordination and the Peter and Garrett's development routine, notion of alignment?
Pickering and Garrett work with what I call the fast process. I mean, they are basically doing this building up dialogue process. How you do the alignment there. I mean, they're giving a model of Herbert Clark's ground, building up a common ground, and they have a bit more precision that he has in the model. Now, that process is different from this slow process of coordinating a fixed point of meaning, which takes a longer time, which builds on a society with a lot of communication way and so on. But even in the fast process, you may have successes and failures. I mean, I may talk about use the pronoun he, and you've forgotten and you don't understand what I'm referring to. And then they would say that that's a break. You give me some feedback. I have to specify who I'm referring to and so on. But I mean, basically, they're doing what I call the fast process. They're not doing semantics. They're doing the pragmatic process of alignment during a dialogue. Yeah.
Just a quick question about the notion of fitness. So it's a property of the conceptual space. So my question is that we assume this property and then we reach to the convexity, or because of the convexity we realize that fitness is working.
You can use, but it doesn't matter very much where you start. Yeah. You can define between it in terms of convexity. You can do that. But basically, similarity. Well, similarity is not between us, but you can say that one color is between another one. People make that kind of between color B is between color A and C. I mean, people make that kind of judgments, size or whatever. Yeah. Okay, that's okay. One more.
I don't know whether, I'm struggling with the term use space and domain. How it relates to each other? Is the question. Domain and space, do they? Just.
Okay. Yeah. No, I'm being a bit sloppy here. A domain is a specific thing like a color or a shape or a size or whatever, and a space is a product of domains. So you can have, when you talk about objects, the bird space is a product of several domains and so on. Each domain has a number of dimensions. Color space has 3 dimensions. Shape space, I don't know how many dimensions it has, and so on. So for me, I use the term space a little bit sloppily here. I agree to that. But basically, it's a product of domains. That would be my more formal definition. But I agree. I use space too often, I guess. Now I have 50 more minutes, I suppose, to start on the major topics on my talk. I mean, what I've said up to now is a kind of preparation. I've set a foundation for what I mean by semantic theory. I answered most of the 6 questions I gave at the beginning. Now we get into this problem of explaining why we have word classes and what are their semantic contents. So, why do we have word classes? So these are some examples of what you learn about word classes in school. There are lots of them, and there are different ways of defining them. And actually, there is no universal classification of word classes. The word classes we learn about school work best for Indo-European languages. They derive from Sanskrit scholars, and then they've been modified by Latin scholars, and then we've taken over these categories in our. So if you try to apply these Indo-European word classes to other languages, it may not fit very well. And there, you had this example on categories. I mean, nouns in Cree that didn't fit your intuition. So, I mean, there are problems, but I don't want to get into, I'm not a comparative linguist. I will assume that we work with these word classes that we get from Indo-European languages. And even within we carve up things in different ways. I mean, some languages use more nouns and other more verbs in different ways. I'll get in that. And as I said at the beginning, when you take linguistic courses, the word classes are defined syntactically. So nouns are things that can have plurals, and verbs define. I don't know what is the syntactic definition of and an adjective is a modifier of a noun phrase. I don't know what, but the word classes are defined by their syntactic properties. When you learn about word classes in school, I mean, in particular, if you go to primary school, you learn that nouns are about things, adjectives are about properties, verbs are about actions, and so on. You get this kind of semantic modeling or description of the word classes. And I want to get back to that. I think there is a lot of sense in doing that. So this is my aim in this part of the talk, to give a cognitive and to some extent communicative motivation for why we have these word classes. Now I get back a little bit of repetition here, what I mean by an object category. And I already said that there is, for an object category like apple or horse or chair, there is a set of relevant domains. And as I explained, this set of domains may be expanded as you learn more about the concept. Set of convex regions, I already talked about that. And some of them you have different weights of the domains depending on the context. To take the English words roe and caviar, they denote exactly the same things, namely fish, eggs. So when do you use the term roe? Well, that's in the biological context, when you talk about the reproduction of the fish and so on. And you use the word caviar if you talk about food, when a roe turns into food. So it's a different context, but the extension, the things in the world are exactly the same. Okay, that depends on there are salience weights for the domains. We talked a little bit about that. And I already said that. So, okay, this is basically a repetition of what I said earlier here. I didn't talk very much about part-whole relations, but that's also included in the definition. I don't have a very good description of how to model part-whole relations in conceptual spaces. I've made some attempts, but that's to some extent still an unsolved problem, how to describe that dogs have 4 legs and stuff like that. Now, the reason I repeat this is that nouns, not all nouns, but the nouns that kids learn first are based on object categories. Kids learn, the first nouns that they learn are about object categories. So I want to use that as the semantic basis for nouns. I don't say that this is all that is included in nouns. I will get back to that in a few minutes. So there are information for several. Now, one question is, of course, what domains are important for a category like dog? I mean, the shape of a dog is quite central. Maybe the sound of a dog. I don't know whether smell of a dog is so important. The temperature of a dog is not important in categorizing dog, and maybe color is a little bit important. So I mean, when there are certain domains that are more essential than others. I talked a little bit about that already. But we can look at what's called definitional generics. I mean, a dog has 4 legs. It's part of the meaning, so to speak. The cup has a color. But if you look at an idea, now we get into an abstract concept here. To say that an idea has a color doesn't work, because idea is a concept, is a noun that doesn't have that domain, doesn't include the color domain as part of its meaning. So different nouns are associated with different domains. So that's a first lesson to learn here. And they are more or less salient, or I don't want to use essential here, because there is a philosophical tradition of essentialism that a dog essentially has 4 legs, but I know many dogs without 4 legs, so that doesn't really work. Then we can also look at individual objects, a single object. And a single object can be described as a point in a space. It has a particular size, length, and width. It has a particular weight. It has a particular temperature. It has lots of properties. So if you have a very rich conceptual space, including all domains you want to talk about, an object would be a single point in the space. You specify all the properties. And mathematically, an object is a degenerate region. I mean, it's a region with only one point. You can think of it, and it's by automaticity, it is convex. The important thing here is that the properties are always consistent. You don't have an object that is both red and green. You don't have an object that is both hot and cold, and so on. As a point, you have some kind of consistent combination of properties. If you go to traditional analytic philosophy, then you have to introduce what is called meaning postulates, saying that green things are not red and red things are not green. You have to have these kinds of postulates to make sure that you don't get conflicts between the different properties. And many points represent merely possible objects. We can combine properties in many different ways and create objects that don't exist in the real world. I mean, I already mentioned unicorns. We can have shape space. I mean, in a certain part of shape space there are unicorns. In other parts of shape space there are sphinxes and I don't know what. I mean, all those fantasy centaurs and other fantasy animals. They are possible because they are possible shapes according to shape space and other properties. I don't think that a centaur is a very good biologically, because having both 4 legs and 2 arms would make you an insect, but that's not well, it's a biological problem of getting the thing to work. But anyway, and this is a very simple model of fictionality. We can talk about objects that have properties that don't exist in the world, but if the properties are still consistent, they are possible objects. Then physical objects are special. They are supposed to be spatio-temporal continuous. And that means that this bottle is only at one place. And in thousands of seconds from here on, it's not in New York at the same time. It can't move that quickly and so on. There is a kind of spatial-temporal continuity. Our minds, now we talk a little bit of psychology, or child psychology, works according to what's called object permanence. That is, if I do like this, you still think that your bottle exists, because there is a spatial temporal continuity, and you are not surprised if it comes back again, because in your mind you have object permanence. We are not born with this. Children have to develop the object permanence. But this is something I could model this, because a physical object has a location. And I can follow the trajectory of an object in space, in the product space of space and time. And then the object permanence then means that this trajectory is a continuous path. That's what it means. So I can give some kind of modeling in terms of conceptual spaces. Now, I already said that, well, I talked about nouns, but now the basic semantics of nouns and names is their communicative function is to identify a referent. And Michel talked about these communication games in robots where you have to identify the yellow triangle and so on. That's the object. What are these games called? I mean, the naming games or naming games. Yeah. I mean, we do that. I mean, give me the blue bottle. I mean, we do that all the time. We use nouns and well, adjectives. I get to that as identifying reference. And or the name. Give me, I don't have a good name. Well, I could say, Lucas, come here. I mean, I use Lucas to identify an individual, to identify a name here. And nouns refer to object categories. I already said that. Names refer to object, to singular. But still, I mean, nouns and names functions grammatically quite similarly, and they have lots of similarities. So names I would see as degenerate radians, one single point. Now, nouns don't identify unique reference. I mean, if I say, give me the bottle, you wouldn't know which bottle I'm meaning here. I mean, if I want the left one or the right one, the one with the dark blue or the light blue cap, you wouldn't know if I just say the bottle here. So nouns are not perfect as communication devices. If I had called this one Adam and this one Bob, I could have said, give me Adam. And then you would have known if I had given them names. I could do that. So why don't everything have a name? Then we would solve the referentiality problem. Well, the obvious answer is that our memories wouldn't solve this problem. Nouns are cognitively economical. I can use a general term like bottle to identify a small subgroup. I mean, I could, and by pointing, I can add information. I mean, pointing is like having an adjective on top of it. Nouns are cognitively economical. And I gave you the story of prototypes. I mean, prototypes give you a way of dividing the world into a fairly small number of categories or regions, and that will help you to identify what I mean when I say the word bottle or chair or whatever. So that's the point of having nouns. I mean, we have nouns because they give us help. They offload our memories. Instead of having names for everything, nouns will make it easier for us to remember how to use different words. Now, I get into, this will be my last topic here, into how we can use the idea of domains to give subclasses of nouns. And there are actually quite, I mean, it hasn't been studied very much. And I can do a little bit of work here. So if you talk about the place, about the Osnabrück or the main square or whatever, they only require the space domain. I don't need anything but the location to identify a place. I can give it more dimensions. I can say that it's a big place. I can say it's a nice place, or it's whatever. It's dangerous. I can add more. But basically, places only rely on the space domain. Mass nouns. What distinguishes mass nouns from count nouns? Masses don't have shapes. I haven't seen this distinction in the literature, but it's a very simple way of identifying what is a mass noun. It's something that doesn't have to have a shape. Concrete nouns, they require object category domains, and object category names are sizes, shapes, weights, temperatures. I mean, all these domains that are associated with physical objects. This is what I talked about, the perceptual stuff we talked about earlier. And one thing that characterizes abstract nouns is that they don't have a location. I mean, objects, concrete nouns, they have locations. Things have locations in space. Abstract ideas don't have locations. They don't have any values on the space. I can say that this idea is in my head, but that's well. Agents require the force domain. The agents are supposed to act. And actions means that you can exert some kind of force, and I will get back to that when I get to verbs. An intentional agent has to have goals. You have to some representation of goal domains. I haven't talked about the goal domain, but I can point to Michael's talk here where you talked about moving from one space to another. It's a representation of where you want the thing to be located, or what properties you want to change of a thing. You can represent goal domains. So if I sum this up, now I have an ugly picture, and this is a picture I'm working on. And I would need some help in doing this a bit better. But basically, what I do, I sort nouns into different types here. Place nouns, concrete nouns, mass nouns, abstract, the ones I talked about. And then we have different domains here. Space domain, object categories, domains that I talked about, size, shape, and so on. Material, whether it's gold or water, shape space, force space, emotion space, goal space, and maybe other mental spaces. And then we can see that different types of nouns require different domains. So a place noun needs, plus means it's more or less essential, and plus means that it often occurs. Question mark means that it's optional, and minus means that it's impossible. So that's the signs here. So place needs space location, can have some other properties. Concrete, yeah, you can talk about where it's located, but it needs these properties. Mass noun forbids shape here. That's the important distinction here. Abstract nouns don't have these properties. I don't know whether abstract nouns have shapes. I mean, these are optional, I think. Agentive needs the force domain, intentional needs the goal domain. So what I'm doing here, by looking at what domains are the central ones for different types of domains, I get the classification of nouns. And now, down here are a list of adjectives that go with the different domains. So there are space adjectives, there are object category domains, and so on. And the point here is that given this sorting of adjectives, I can use the minus signs to make predictions about impossible combinations of adjectives and nouns. So to give you examples here, round water doesn't work because water is a mass noun, and mass nouns don't have shape. You can't talk about round water. You can't talk about happy gold because happy is an intentional thing, and gold doesn't have any values on the emotional domains. You can't talk about a strong garden. A garden, a place, is a place it can't exert any force. You can't talk about red happiness because happiness don't have these properties. I mean, of course, there are metaphorical uses of this. I mean, but basically, given this categorization of nouns in terms of what domains they allow, what the domains they require, and what domains they prohibit, I can make empirical predictions about what adjective nouns combinations you will not find in languages. But this is, I mean, as I said, this is just a very early attempt to do a classification of. I mean, this probably needs a lot more work and a lot more specification of what's included in these classes. But it's a first attempt, and that's a work I'm involved in. I haven't really finished it. Sorry, I'm going the wrong direction. Some languages, like Japanese, have these noun classifiers. So certain you have to have certain endings here. So you have things that mark cylindrical things, flat things. These are shape classifiers. You have these marks living things and so on. There are different suffixes that are used to tell about the noun class here. And my question, I mean, I don't know enough about these languages to answer it myself, is whether you can do a similar story about these noun classifiers in terms of what are the domains that are involved in these noun classifiers. That's a kind of hypothesis from my point of view, that we can use the idea of domains to analyze these noun classifiers. But I give that as a task to the linguist in the room here to do that thing. Okay, I'll stop here because now I'm finished with nouns. And tomorrow we continue with the other word classes.